So exploring probability. So the first thing we've got here is the definition of a fair game. Sasha and Mika have to invent a fair game, and that is a game in which all the players are equally likely to win. For example, tossing a coin, calling heads or tails. That's a fair game, right? As long as it's a fair coin. Okay? In other words, it will come up heads or tails equally likely. Most of the coins you rock around within your pocket are fair coins, right? Like they're not balanced or weighted to come up one way more than another. If you're playing dice games, you want fair dice, right? So if you go to a casino, they always make sure that the dice are good. You can't cup the dice like that, right? You can't make them invisible because you could palm them and replace them. So you always have to hold the dice so they're visible. And the dice are clear, okay? So you can see through to see if they're weighted or not, right? You can put weights in the dice so that it comes up more often one way or the other. That would be an example of something that is not fair and would lead to an unfair game, right? So if you're playing dice in a back alley somewhere, you gotta watch out. I mean, it might be loaded dice. Anyway, here are the rules. 2 people play. Each player has a container. Both players put 3 identical slips of paper numbered 1, 2, and 3 into their own container, right? So your little container's got slip paper 1, 2, 3. For each turn, both players draw 1 slip of paper from their container. So you're either going to get the number 1, the number 2, or the number 3. Player 1 scores a point if the product of the 2 numbers drawn is less than their sum. So for example, if they have a 1 and a 2, their product is 2, but their sum is 3. Okay, and so if the product drawn is less than the sum, then they'll win. Player number 2 scores a point if the product of the 2 numbers drawn is greater than the sum. Okay, so if it's a 1 and a 1, then the product is a 1 and the sum is a 2, so this guy would score. Anyways, neither player gets a point if the product and sum are equal. And after each turn, the players return their slips of paper to their container, and a game consists of 10 turns. Question is this a fair game? And if not, why not? So to do this, we have to look at the set of all possible outcomes, right? And we'd have to say, okay, which outcomes are good for player 1, which outcomes are good for player 2? So if we think about it, way of listing a set of outcomes, right, and this goes back a couple of chapters, right, to set theory. We have to do a set. And maybe counting. Okay, how many possibilities are there? So there's 3 possibilities for the first and 3 possibilities for the second, which gives a total number of possibilities of fundamental counting principle. 3 times 3, 9. Okay, so there's 9 outcomes in this thing, right? So, if we wanted to draw a tree diagram, we could say, player 1 can get a 1, a 2, or a 3. If player 1 gets a 1, player 2 can get a 1, a 2, or a 3. Okay, and then we can list all of these outcomes, right? So the outcomes are, let's just list them over here. So we got a set of outcomes. 1, 1, 1, 2, 1, 3, 2, 1. Actually, you know what? Let's list them going down. So let's do it this way. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And the reason I want to do it this way is because we're interested in the product and the sum, right? So now we can set up a couple of columns. So basically what we're doing is conducting an analysis of this game, right? So we got product, and we got sum, and let's do 2 other things, right? Wow. I'll undo that. Too close to the top. Product, sum, and then from that, let's decide who scores and how much they score. Okay, so then we've got player 1 and player 2. Okay, so this way we're doing a full analysis of this game, right? We have listed every possible outcome there is. There are 9 outcomes, right? 3 for the first player times 3 for the second player is a total of 9. Products, this is 1, 2, 3, 2, 4, 6, 3, 6, 9. Sums, 2, 3, 4, 3, 4, 5, 4, 5, 6. Okay, player 1 scores a point if the product is less than the sum. Product less than sum, okay. Product less than sum. Product less than sum. Product less than sum. Equal, greater. Product less than sum. Okay, player 2 scores a point if the product is greater than the sum. Okay, so no, equal, so nobody scores a point if they're equal. Product is greater than sum. Product is greater. Product is greater. Okay, so how many times? Of the 9 turns, player 1, 2, 3, 4, 5 will score on 5 of the 9 turns, right? So it scores on 5. Player 2 scores on 3 of the 9 turns, and nobody scores if it's a 2 and a 2. So is this a fair game? No. Right? I mean, player 1 is going to win. Right? They have, you know, for every 9 turns, they're going to score a point on 5 of those 9 turns. Okay, so is Sasha's game a fair game? No. How do we know? We ran an analysis, right? We went through every possibility, and we said, no, this is what's going to happen. Is playing Sasha's game once a good way to decide if it's fair? So let's say you actually played it and you just went through one round 10 times. Would that be enough to say, no, this isn't fair? Yeah, maybe it would give you an inkling that it's not fair, but you don't really know if you just do it one time. So what would you have to do? You have to play a bunch of times, right? So if you played, you know, 10 or 20 or 30 rounds and you found out, hey, player 1 is winning every round, then you could be pretty sure this is not a fair game, right? Mika says you can use theoretical probability to determine, and when you play the game, would you rather be player 1 or 2? Well, depends if you want to win or lose, right? So if we actually played the game a number of times, then we would be conducting an experiment. And that's called experimental probability. So, key ideas. Knowing the probability of an event is useful when making decisions. The experimental probability of an event is represented as P of A is N of A over N of T. So N of A is the number of times event A occurs, and N of T is the total number of trials in the experiment. Okay, so it's how many times something happened over the total number of outcomes. The theoretical probability, so theoretically we could say you're going to win 5 out of 9 times, right? There are 9 possible outcomes. Player 1 will win 5 out of 9. Player 2 will win 3 out of 9, and nobody will win 1 out of 9 times, right? Now, we could do experiments, conduct an experiment a number of times and find out, and eventually if we did enough experiments, we should come up with those same numbers, right? 5 out of 9. If you have a large enough set of events. So if you're doing experimental probability, you just need to do it a lot. Theoretical probability is where you can actually analyze the game, right? And that's what we did. We listed all the possible outcomes. We looked at the outcomes and how that affected the scores. And then we can say, hey, 5 out of 9 times player 1 is going to score. 3 out of 9 times player 2 is going to score. And 1 out of 9 times nobody is going to score, right? Over the long run. Theoretical probability is P is N of A, number of favorable outcomes for the event, and the total number of outcomes in the sample space. Okay, so that's what we've counted out. So basically, the definition of probability, so here's the short one. It's favorable over total. And by favorable over total, I mean the number of favorable events, right? The ones where what you want to happen happens, and the total is the total number of outcomes that there are. So probability is favorable over total. How many times player 1 scores? 5 out of the total number of outcomes, 9. That's your theoretical probability. So when I say favorable, I really mean number of favorable over the number of total. Mostly, we're going to examine things that have theoretical probabilities, right? So any card game There are theoretical probabilities. You know, or you can work out the probability of a certain thing happening, right? You ever leave the sports channel on late at night and all of a sudden it's poker, because that must be a sport. But you'll see, as they play through the hands, you'll see these probabilities coming up underneath, right? And it'll say, oh, so-and-so has like a 100% probability of winning, right? Now, they can't lose. There are no cards that could come out which are going to cause them to lose, right? And sometimes it just flips around, right? It's like somebody's got like an 11% chance and the other guy's got an 89% chance, and then all of a sudden this card comes out and boom, it goes 100 to 0, right? Like that guy just won. He got the one card in the deck that he needed in order to win. Okay, so these probabilities change throughout, but they can all be calculated, right? And so they just have computers working on it, right? They just say, oh, well, the chance of this happening is this, and therefore that's the probability of them winning. A game is fair when all players are equally likely to win. Need to know, an event is a collection of outcomes that satisfy a specific condition. Okay, this goes back to set theory. Okay, event and outcomes. For example, when throwing a standard die, the event, throw an odd number, is a collection of the outcomes 1, 3, and 5. Okay, standard die is one 6-sided die, right? Numbers are 1, 2, 3, 4, 5, 6. The probability of an event can range from 0, impossible, to 1, certain. You can express probability as a fraction, a decimal, or a percent. Okay. Now, oftentimes what we'll do is we'll start off as a fraction, and then we'll reduce the fraction. So we'll calculate the fraction, but we'll do it actually by counting, right? So unit 2, counting. Right? So unit 1, set theory, or the 2 units ago we did set theory, then we did counting. So when we do our probabilities, we're going to do it by counting sometimes, right? And we will get the actual counts, right? There are 26 black cards out of 52 cards. So the probability of drawing a black card is 26 out of 52, and then we'll reduce that to 1/2. Sometimes we don't want to reduce these probabilities because we may have to add them together, in which case, if I'm dealing with cards, I really want to have everything out of 52, right? Because then I'll have a common denominator. I don't want to say, oh yeah, the probability of getting a black card is 1/2. The probability of getting a spade is 1 out of 13, and I need to add those together. Well, then I got to convert the 1 out of 13 back to 4 out of 52, right? So that I can add those. You can use theoretical probability to determine the likelihood that an event will happen. Okay? That doesn't mean it's going to happen. It doesn't mean it's going to happen on the next flip of the coin or something. That's the gambler's fallacy, right? It's like you flip a coin, you have a fair coin, you flip it 10 times in a row, it comes up heads. So what's it got to be the next time? Got to be tails, right? Got to be. Can't come up 11 times in a row. The probability of it coming up heads 11 times in a row is really small. Doesn't have to be anything, right? It's 50-50. Probability of it coming up heads the 11th time, if there were 10 in a row, is 1/2. If it's a fair coin, comes up 1/2. How can you change Sasha's game so it's fair? Well, we need to take one of the events where they were getting 5 and move it over to the other column, right? So that it becomes 4 and 4. So right now it's 5 out of 9 for player 1, 3 out of 9 for player 2, 1 out of 9, nobody. If we can take one of the events from player 1 and get it down to 4 out of 9 and give that to player 2, so they're also 4 out of 9, then the game is fair, right? They have an equal chance. Consider each game below. Is it fair? If it's not, who has the advantage? Matt and Pat each toss a coin. If the coins land as both heads or both tails, Matt wins. If the coins land as a head and a tail, Pat wins. Fair or not fair? Life isn't fair either, but this game is. So how would we figure out if it's fair? We'd have to list the outcomes, right? And we'd have to say, so, same deal. So how can we list the outcomes with the two heads, right? Well, we could say, well, you flip the coin, it's heads or tails. Then you flip again, or you flip another coin. And then list your outcomes, right? So what are the outcomes? 2 heads. Who wins if it's 2 heads? Matt. Okay. Head, tail. Who wins if it's a head and a tail? Pat. Tail, head. Who wins if it's a tail and a head? And tail, tail. Who wins if it's 2 tails? Okay. So Matt wins twice, Pat wins twice. right? And tail-head is different from head-tail, right? So sometimes you might want to take this set and say you either get 2 heads or 2 tails or 1 of each, right? So you're implying there are 3 outcomes. Both heads, both tails, or 1 of each. And that's, in a sense, that's true. But the 1 of each, it matters what order, right? I mean, if you've got a penny and a nickel, then is the penny heads and the nickel tails, or vice versa? Those are actually 2 different outcomes. So that's why listing a sample space is often very helpful in doing probability, right? So you don't fall into that trap of, oh, well, it's either both heads, both tails, or 1 of each. So the guy that had 2 heads or 2 tails, he wins on 2, and the other guy only wins on 1, right? Because you're thinking there's only 3 outcomes, but there's not. Trina, Lena, and Gina each toss a coin. If all 3 coins land as heads, Trina wins. If all 3 coins land as tails, Lena wins. Otherwise, Gina wins. So who do you want to be of that group? If winning matters. Yeah, you want to be Gina, right? Because how many ways? So again, think about it, right? Like, how many outcomes are there with 3 coins? Coin number 1, how many ways can it come up? 2. Coin number 2, how many ways can it come up? Coin number 3, how many ways can it come up? How many outcomes are there? There are 8. How many of those are all heads? Only 1. How many of those are all tails? Only 1. So Trina and Lena each have a 1 out of 8 chance of winning. What's left? Everything else, 6 out of 8. Right? 3/4 of the time, Gina will win. Not a fair game. Anne and Dan each roll a standard die. If the sum of the 2 dice, okay, you have a pair of dice. What's the lowest sum that you can get? 2. What's the highest sum that you can get? 12. How many outcomes are there? 36, right? 6 times 6. How many of those are a 2? Well, we can get a 2 is to have a 1 and a 1, right? So 1 out of the 36. How many of those are a 12? 1 out of 36, right? Okay. What does the question say? If the sum is, if the sum of the 2 dice is greater than 7, Anne wins. Less than 7, Dan wins. If the sum is 7, they tie. Fair game or no fair game? It's not fair that you guys don't get any of these right. But that's the way life is, so it is a fair game. There are as many sums below 7 as there are above 7. Right? There's 6 ways of getting a 7. We'll go into this in more detail over the course of this, right? Before you walk into that casino and pick up the dice, you should have some idea what you're doing, right? Which is you're going to lose. Otherwise, casinos wouldn't exist if people didn't lose. If people won all the time, then casinos would go to business. So, yeah, we'll look into this in more detail as to how the outcomes for a set of dice. We'll look into applying some of the stuff we did with counting to working out probabilities of poker hands, right? Poker hands are ranked based on probabilities, right? In order to do probabilities, which we now know is favorable over total, wherever that went. I have no idea where that went. Probably at the top of this page. Oh, probability is favorable over total. So in order to do that, you have to count. Okay, so this game is fair. Everard says he has a 120% chance of making the school football team. Is this possible? No. What's the highest that his percentage chance could be? 100, okay? Now, you may tell the coach that you will give 110%, but in probabilities, you can only go up to 100%. Okay? Mika suggests playing Sasha's game with 4 slips of paper numbered 1 to 4. Is it now fair? How many outcomes would there be? 16, right? I'm not going to go into the game. We'd have to sit down, list all the 16 possible outcomes, figure out if the products and the sums match, right? But we could do the analysis, right? And that's the whole idea behind probability is you have the ability to do the analysis, right? On events that have theoretical probabilities, like flipping a coin. Okay, if I flip this coin, it's going to come up heads or it's going to come up tails, right? If you accidentally drop your coffee cup, how could it land? Could land right side up, right? You go, ooh, thank God, and you pick it up and continue drinking. Could land upside down. How else could it land? Could land on its side. What's most likely? Side. How do you know? Since the time you were this big, you've conducted the drop a cup experiment many times, right? And your experimental probability tells you that thing's going to land on its side. Anybody ever push a cup off the table and have it stick the landing? Or just go, right, and nothing spilled? Anyone? Yeah, so once, right? All right? It doesn't happen that often, right? I mean, you'd notice that. You'd go, whoa, like, you know, wow, that shouldn't have happened, or that's never happened before, right? Because experimentally, that doesn't happen. Can we do a theoretical probability with the cup drop? Yeah. You guys are batting like 0 for answering questions so far. No, not really, right? Because we don't know. You know, I mean, unless we could do some analysis of air currents and gravitational fields and how high is the table and how, you know, how is it being pushed off? Like, is it being pushed off, you know, like vigorously, in which case it's likely just going to fly and land, or is it just accidentally just pushed off just a little and just sort of dropped? Was it pushed a little so that it just lost its balance? In that case, you know it's going over. Okay, or was it just knocked off like this, in which case it might land like that? So we don't know, right? There's no way to be able to do that. We would have to conduct the experiment many times, and then we could come up with a probability, right? Say, okay, we did this 1,000 times, 900 times it landed on its side, you know, 15 times it landed upside down, and maybe 5 times, whatever, right? And that would give us probabilities, but they would be experimental. All right, we've answered all of these questions. Okay, probability and odds. So, everybody heard of odds? You've all heard of odds, right? I mean, if you, what are the odds? Yeah, people say, what are the odds, right? Now you're actually going to find out what that means. If somebody quotes odds to you, you'll know. Oh, yeah, like, you know, I had the TV on the other day, the Kentucky Derby was on, and they were quoting the odds, right? So odds is related to probability, right? And we need to, well, we don't, you need to be able to convert back and forth between odds and probabilities, okay? And that's what we're going to do today. So, an oil and vinegar salad dressing is made using 2 parts of oil to 1 part of vinegar. The ratio of oil to vinegar is 2 to 1. What fraction of the dressing is oil? Yeah. Yeah. Have fun. Win. What are the odds? No, I don't know. I think they got a pretty good team, don't they? Okay.
I don't know if the players today.
Yeah. Who are they playing?
St. Francis.
Francis? They're not good at rugby, though, are they? Oh, this year. Okay. What fraction of the dressing is oil? I have 2 parts oil. I have 1 part vinegar. 2 parts oil, 1 part vinegar. 2. How many parts are there in total? What fraction is oil? 2/3. 2/3, right? So the ratio is like the odds. All right, suppose at the beginning of the regular CFL season, the Saskatchewan Roughriders are given a 25% chance of winning the Grey Cup. What are the odds of the Roughriders winning the Grey Cup? So, what is the event in the situation described above? So the event is Saskatchewan wins the Grey Cup. Express the probability this event will occur as a fraction out of 100. Okay, favorable. So probability is favorable over total. What's favorable for them winning based on this question? 25. And what's the total? Okay, so 25 out of 100. And what's that equal to? 1/4. So I like to call the 25 out of 100, I call that the raw probability. That's just using the numbers they gave us. And then the 1/4 is the reduced probability, right? Expressed as a reduced fraction. Describe the complement of this event. So the event is Saskatchewan wins the Grey Cup. What's the complement? No. Saskatchewan does not win the Grey Cup. So SK does not win the Grey Cup. Express the probability that the complement will occur as a fraction out of 100. So, what's the favorable of them not winning? 75 out of 100. which is equal to 3/4. Write the odds in favor. Okay, luckily they define what the odds are. So here's what the odds are. The odds in favor, the ratio of the probability that an event will occur to the probability that the event will not occur, or the ratio of the number of favorable outcomes to the number of unfavorable. So probability is favorable outcomes over total. Odds is favorable to unfavorable. Okay, so if we're doing the odds in favor, we're saying it's 25 in favor and 75 against. Now you can reduce those odds because they're both divisible by 25, or by getting a better team, and then you can reduce the odds. But that's 1 to 3. Okay, so it says for every 1 chance of winning, they have 3 chances of losing. Write the odds against. Odds against, the ratio of the probability that an event will not occur to the probability the event will occur. Now they do it as probabilities. I just like to do it as the numbers, right? So it's going to be 75 against them winning, 25 for. So odds for, favorable, 25 they win, 75 they lose. Odds against, 75 they lose, 25 they win. And this becomes 3 to 1. Okay, so if they say the odds are 3 to 1 against, then that means that, you know, it's not as likely to happen, right? There's 3 chances of not winning for every 1 chance of winning. How are the odds in favor of the Rough Riders winning related to the odds against them winning? Just reversed, right? So odds favor, odds against are simply reversed. How does the probability of an event and the probability of its complement relate to the odds in favor of the event occurring? So, you look at the probability of the event, right? We've got 1/4. So here's how you do it. The number up top, this guy, that's always the favorable for whatever the event is, right? In this case, favorable is you will win, and in this case, favorable is you will lose. Okay? So don't think it's favorable. Favorable is good, right? No, favorable is just what I want to happen happens. If I want them to win, favorable is them winning. If I want them to lose, which, it being Saskatchewan, I do, then favorable is they don't win. Okay? So don't ever mistake favorable or the number up top as being, oh, that's the good one, right? That's simply the thing we wanted to happen happens. The bottom number is total. So how would you find unfavorable if you had favorable in total? You might want to reverse that operation, but yeah, you want to subtract the favorable from the total, right? And that will give you unfavorable. And that's how you're going to turn a probability into odds, bless you. And that's also how you're going to turn odds into probability. Okay, so let's take a look at some examples of this and we'll see, right? So we need to, by the end of this, we need to be able to look at the odds, turn it into a probability, right? Odds in favor or odds against, and look at probabilities and turn them into odds. Bailey holds all the hearts from a standard deck of 52 playing cards. He asks Morgan to choose a single card without looking. Determine the odds in favor of Morgan choosing a face card. Okay, so remember, odds in favor of choosing a face card would be, so remember, odds in favor are favorable to unfavorable. So how many face cards are there? There are 3 face cards, right? Jack, Queen, King. That's favorable. How many non-face cards are there? All the rest of the 13 cards are, so how many are not face cards? 10. So the odds in favor of Morgan choosing a face card are 3 to 10. What's the probability? 3 over 13. So to get a probability, if you have odds in favor, you take favorable, which is 3, over total, and if you have odds, the total is you add up these two numbers. So the probability is 3 out of 13. Okay? If you're given probability, you go 3 in favor, 13 total, 3 in favor, 13 minus 3, or 10 unfavorable. That gives me my odds, right? I take the favorable, 2, and I take this away from that. Okay? So probability is favorable over total, odds are favorable to unfavorable. Right? Or vice versa if you're doing odds against. So here, blah, blah, solution, did that, looked at that, lots of writing, 3 to 10. Determine the odds against Morgan drawing a face card. Odds against, you just flip it, right? So odds against. So now what's favorable now? Not getting a face card. How many non-face cards are there? 10. How many face cards are there? 3. Okay. Compare the odds in favor of this event to the odds against. Do you think Morgan is more likely to draw a face card or something different? Something different, right? I mean, there's 10 different cards, only 3 that match the criteria. All right. Determining odds and probability. Research shows, I think this number might actually be accurate. You know, you can never tell in math books. That the probability of an expectant mother selected at random having twins is 1 out of 32. What are the odds in favor of an expectant mother having twins? Okay, what are they? You have the skills now.
1 to 31.
1 to 31, right? So odds in favor of having twins, that's favorable, is 1. Total is 32, which means there are 31 non-twins, right, out of the 32. These two guys have to add up to the total. What are the odds against having twins? 31 to 1, right? You're just reversing it. And then here's a whole pile of words leading to the same stuff. Suppose the probability of an event happening is 2 out of 5. What are the odds in favor? 2 to...
3.
Okay, so put the clutch in first, then shift it into gear, and then say it. You're less likely to just blurt out 5. What are the odds against this event happening? 3 to 2. Okay, if I had given you the probability of 2 to 5 and just asked you odds against, then what you should do really is just work out odds in favor. Just say, hey, wait, it's 2 to 3, and then just flip that around and get 3 to 2, right? Like that's the easiest way to do it. Because you've got the 2 already there. You go 5 minus 2, you get the 3, and then you say, but they wanted the other way around. They wanted the odds against, so I'm just going to go 3 to 2. Computer randomly selects the university student's name from the university database to award a $100 gift certificate for the bookstore. The odds against the student selected being male are 57 to 43. Okay, so what do we have? 57 what? And 43 what? 57 females, right? The odds against the student being male, right? So then the unfavorable would be the males. Favorable would be the females. So we got 57 female, 43 males. Determine the probability that the student will be male. So probability is favorable. How many males? Out of total. So 43 out of 100. 43%. 43%. Or 0.43, right? Probability can be expressed 3 different ways, right? Fraction, percentage, and decimal. Yeah, exactly. So fraction and percent, decimal. Decimals go from 0 to 1, percents go from 0 to 100, and fraction goes from 0 to 1. All right, number of males, blah, 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 57 female, 43 male, right? So when you're doing these questions, just take your time, read the question, figure this odds in favor figure out what that first number is. What does it represent? The number of face cards, is it the number of nails, whatever. Oh, they gave me odds against. We can always flip it and just say that it's 43 to 57 that it is a male. Right? The odds against to be male, 57-43, then male is 43-57. Okay, probability is 43 out of, and take the total. Suppose the odds in favor are 5 to 3. Is the probability the event will happen greater or less than 50%? Bless you. So what's the probability? So odds in favor are 5 to 3. The probability event is 5 over just 62.5%. Okay. Making a decision based on odds and probability, right? So this is where you have to, in life sometimes we want to know, okay, what's the probability? What are the odds? I have to make a decision, and what am I going to base that on? So here, a hockey game is ended in a tie after a 5-minute overtime period, so the winner will be decided by a shootout. Coach must decide whether Ellen or Brittany should go first in the shootout. Okay, so anything in sports, there is a ton of numbers around sports, right? So that means the coach, really should be somebody sitting on the bench with a computer who can feed the coach that, hey, this is how so-and-so is playing this game. This is how they've done against this goalie, right? In baseball, it's like, how do they hit against right-handed pitchers on a Wednesday when it's raining? Right? And they have that information. Okay, so how do they hit against this pitcher, right? How does this pitcher pitch against, who do I bring in to pitch against this guy? So all that information is there, right? And they use that to make decisions. Anyways, coach must decide whether Ellen or Brittany, the coach would prefer to use her best shooter first, so she will base her decision on the player's shootout records. So Ellen has 13 attempts and has scored 8 goals. Brittany has 17 attempts and has scored 10 goals. Who goes first? So what's the probability of Ellen scoring? Okay, well, let's get a fraction first because we got to work with the numbers we got. So what do we do with the 8 and the 13? So she scored 8 out of 13, right? What's 8 out of 13 as a decimal? 0.615. What's the probability of Brittany scoring? What are the numbers first? Give me the fraction. You can't do that. 10 out of 17. You can't have a probability greater than 1. What's 10 out of 17? Who goes first? Ellen. Okay. Not by much, but that's how you do this, right? You could write odds, right? Say, well, the odds of Ellen scoring are 8 to 5, right? Odds. 8 favorable, 13 total, so that means 5 unfavorable. This would be 10 to 7. But if you want to compare 8 to 5 to 10 to 7, you can't do that, right? If I have 8 to 5 and 8 to 7, and 7 to 5, I can compare those. Well, 8 to 5 is better than 7 to 5. But when they're like this, it's like, yeah, I really don't know how to compare that, right? So let's go to a probability. Let's take odds. If you did go to odds or were given the odds, you go 8 out of 5, okay, 8 to 13, add them together, 10 out of 17. You can't really compare 8 out of 13 and 10 out of 17, right? So you need to convert them to decimals or percents, right? Which would just be multiplying by 100, say 61.5%, 58.8%. Okay, who's got the better record? Who goes first? Okay, and we figured out, right? 0.615 and Josie's also on the team. She has scored twice in 3 shootout attempts. Should the coach put her first? 2 out of 3. 0.6 repeating, 0.6 repeating. Should she go first then? She's got a 66.6%.
Yeah.
Wow, yeah, but she doesn't have that much experience, right? So that's where the coach has to come in and make the decision. Yeah, you technically you have a better shooting percent, but you've only made 3 attempts, right? So I'm going to go with person. In a shootout, it may not matter that much because you're going to have at least 3 players shoot out, so it's not just first goal wins kind of thing. It's not like the NFL overtime rules, which are the stupidest overtime rules in existence, but you know. Interpreting odds against and making a decision. So remember, if we see odds against, we can just flip them and get odds in favor, and then it's easier to turn odds in favor into a probability because you've got favorable first, right? Than it is to turn odds against. You can still turn odds against into a probability, but... Okay, a group of grade 12 students holding a charity carnival to support a local animal shelter. The students have created a dice game they called BIM and a card game they called Zap. The odds against winning BIM are 5-2, and the odds against winning Zap are 7-3. Which game should Madison play? So first off, let's convert these to odds in favor of winning. So we have 2-5 and 3-7. Let's convert those to probabilities. This will be what? What's the probability of this? 2 out of 7. And the odds here are 3 out of 10. So you got 0.28, whatever, 2.286, and you got 0.3. So slightly better probability of winning Zap than BIM, right? So there you go. Right, so if you get odds against and you need to do probability, convert them to odds in favor, right? Just flip it. And then take favorable over total. Take the first number over the total of the 2 numbers. Go forward. Samara solution using equivalent rate. Don't do that. That's just not, don't do that. Key ideas. Odds express a level of confidence about the occurrence of an event. Okay? The odds in favor of an event are given by the ratio. Generally, we're not going to do odds as a number over a number, right? We're going to do it as a ratio, this to this. That's how you're going to see the odds stated. P of A to P of A prime. If you're stating odds, you have to have the total number of events has to be split between the 2 things, right? So we can't go to the first one and say the odds are 3-9. Right, or 4-9, because we're not including everything there. So instead, in that one, we would just work out probabilities. Right, and then say the probability of winning that game in 3.1. Simplifies to a ratio favorable to unfavorable. The odds against an event are not occurring, so the prime just means not the event that I want. And P of A is the event that I want. P of A prime is probably the complement of A, where it's 1 minus P of A, right? So if you have 2 events and their probability adds up to 1, then that's all that can happen. Okay, so it either rains or it doesn't rain. It's like bimodal, right? There's 2. The marker can fly or not. Okay, so there's only 2 possible outcomes, right? Either this or that. We can't say dice and say, what are the odds of getting a 1? Unless you define the events as getting a 1 and not getting a 1. Okay, and then you could say 1 out of 1 to 5, right? There's 1, 1, and there's 5 non-1s, and the odds against are 5-1. Probability complement, if the odds in favor of event occurring are m to n, then the odds against are n to m, and if the odds in favor are m to n, then the probability is m over m plus n. So if you're given the odds against, and you got to get a probability, change it to odds in favor, and then just take the first number over the total of the 2 numbers. At this point,